Today we're going to answer the question, how much information does the mean of a random sample give us about the mean of the distribution that sample was drawn from? So suppose that I drew a sample, random sample of 20 students at the college, and I got each of their ages, and so now I know the age of all the students in my sample, and I can compute the average age in my sample. How much does that tell me about the average age of all students at the college? It tells me something. What exactly does it tell me? I don't know for sure because I've only talked to 20 students, not everybody, what the average age of all students at the college is, but I know something. And suppose that I did that, I took a random sample of 20 students. Suppose that you took a random sample of 40 students. Your sample is bigger, and so you should be able to make a better guess at the average age of all students at the college. How much better is your guess than mine? All those things we should be able to quantify and give real rigorous quantitative answers to. So let's do that. So to derive the answer to this question, let's start with this picture here. It's not clear exactly why this is here. It will be in a sec. So just hang on for a sec. I'm going to leave this here. So you're taking the mean of a random sample. And the usual notation for the mean of a random sample from the distribution of a random variable x is x bar, right? And by the central limit theorem, this thing, x bar, this is a random variable which stands for the mean of a random sample from the distribution of x. So by the central limit theorem, this x bar is normally distributed, well, technically is approximately normally distributed with mean mu and standard deviation sigma over root n. That's what the central limit theorem says. As long as you're sampling from a distribution whose mean and standard deviation are defined, and as long as your sample is big enough, then the distribution of the mean of a random sample will be approximately a normal distribution with mean mu, the mean of the distribution you're sampling from, and standard deviation sigma over root n, where sigma is the standard deviation of the distribution you're sampling from, and this n is the size of your sample. Okay, and so if that's true, so that means that if I take this thing, x bar minus mu, divided by sigma over root n, so what I'm doing is I'm taking x bar and I'm standardizing it. I'm taking x bar, I'm subtracting the mean, and I'm dividing by the standard deviation of its distribution. Well, I had a normal distribution before with this mean and this standard deviation. So when I'm doing this, I'm just turning x bar into a z-score. And so when I standardize it, the distribution is going to be normal with mean 0 and standard deviation 1. So that's why I drew this up here, the standard normal distribution. So this little picture up here, this is just a picture of the following statement, that the probability that z, the standard normal random variable, is between minus z star and z star is c. That's what this is a picture of, right? So minus z star and plus z star, these are just two numbers on the horizontal axis. And because one is z star and one is minus z star, they're symmetric about 0. And these are two numbers that enclose an area of c. C is some number between 0 and 1 because it's an area under a PDF. All right? And so it's a probability. So the probability that a normally distributed quantity with mean 0 and standard deviation 1 falls inside these two, in this range, in this interval, is c. Okay? And so because I know that this quantity right here, x bar minus mu over sigma over root n, is normally distributed with mean 0 and standard deviation 1, well, this statement is also true, right? Because the distribution of this thing is the same as the distribution of capital Z. Right? This is also a normally distributed random variable with mean 0 and standard deviation 1. So this statement is still true. Okay. So now all I'm going to do is I'm just going to manipulate this inequality to try and isolate mu in the middle. And it doesn't take that long. I'm going to multiply all three of these things by sigma over root n. Sigma is the standard deviation, which is always a positive thing. N is the sample size, which is always a positive thing. And so this number is a positive number. So when I multiply all three sides with this positive number, it doesn't swap the signs. The signs stay the same. It's important to think about, right, whenever you're dealing with inequalities. When I multiply through, I got to make sure if I'm multiplying by a positive quantity, the signs stay the same. If I'm multiplying by a negative quantity, they change. They flip around. Okay, good. And now, we're almost there. I want to get mu in the middle. So I guess what I'm going to do is, first thing I'm actually going to do is I'm going to deal with the sign on the mu. I'm going to multiply everything by -1 because I want to have a positive sign on the mu. So I multiply everything by -1. Let's see what it does. I end up here, sigma over root n. It flips these signs. Now I have mu minus x bar in the middle. And here I have minus z star, sigma over root n. Okay, so I multiplied by -1. So the signs on every term changed. And in addition, these signs flipped around. So now I'm going to run out of room here. So let me do something in place. I'm going to take this inequality and I'm going to just flip the whole thing around. Like imagine I lifted it off the paper and flipped it around. I'm saying that mu minus x bar is between these two things, right? It's bigger than this one and this is smaller than that one. So I'm just going to write it the other way around. Maybe, okay, I won't do it in place because that'll confuse people. But this is the same thing as this. Mu minus x bar is less than z star sigma over. Okay. So I just wrote these three things in the opposite order, right? If this was like 3 is less than 2 is less, sorry, 3 is bigger than 2 is bigger than 1. I now wrote 1 is smaller than 2 is smaller than 3. Both of these things they're saying the same thing. Okay? This is the smallest of the three things. This is the biggest of the three things. I just changed the order I'm writing them in and changed the signs in a corresponding way. All right. And so finally, the last step to get mu by itself in the middle is to just add x bar to each of these three things. So I end up with the probability x bar minus z star sigma over root n is less than mu is less than x bar plus z star times sigma over root n equals c. Okay, so finally we've arrived where we wanted to be. What do we have? We have probabilistic bounds on where mu is. That's the idea. So for any number c I like, any number c that's going to be a probability, say the c is going to be 90%. If I set c equal to 90, 0.90, 90%, 0.90, then I can find these two numbers, minus z star and plus z star, just using the z table. And I can fill in all this information. I'll know my sample size. If I know the standard deviation in the population that I'm sampling from, I can fill in all this information. And what I'll get is I'll get an interval. My sample mean minus some number, and my sample mean plus some number. And the probability, the mean of the population, falls into that interval is c, which I chose to be 90%. And I can choose c to be anything I want, get the corresponding minus z star and z star, and I'll end up with an interval like this. An interval where mu might fall with a certain probability. So this number right here the number that we add and subtract to the sample mean to make our interval for mu. That number is called the margin of error. And we make a confidence interval, so this thing is called the margin of error. I'll write it down. Margin of error. That's this thing right here. And so the upshot of all this is that you can make a confidence interval for the mean in the whole population by taking the mean in your sample and adding and subtracting this margin of error. And you get to choose this number C. You get to choose the probability that this inequality holds. So let's do an example of this. When you actually apply this, it goes really quick. So we're going to take a sample, compute its mean, figure out this margin of error, and then we'll have an interval of values where we think mu falls with some degree of confidence. So, how do you actually do this? Here's an example. So suppose a random sample of 72 bricks from a factory weighs 164.4 kilograms. Sorry, I think this is should be 162.4 kilograms for this to work out right. And so that means the mean weight in the sample is 2.256. So I just took the total weight of all the bricks in my sample, divided by the number of bricks, and I get the average weight per brick. That's the mean weight of a brick in my sample. If the standard deviation of weights for individual bricks from this factory is known to be 0.15 kilograms, construct a 99% confidence interval for the mean weight of bricks that come from this factory. Okay. And so how do we do that? Here's the procedure. Step 1 is figure out these numbers, minus z star and z star. Step 2 is use those to compute this margin of error, and then we'll add the margin of error to our sample mean to get an interval. Okay? So that because I want a 99% confidence interval, that means I want to be 99% confident that the mean weight for all the bricks that come from this factory falls into that interval. What I'm going to do is I'm going to take this number C to be 99%, 0.99. And that way at the end I'll have the probability of this thing happening to be 0.99. That's what I want. So here I go. Step 1. Let's draw this standard normal distribution. And we want to pick numbers minus z star and z star so that the area in between them in here is 0.99 or 99%. All right? Under the standard normal curve. Okay. So from the z table, you can find out what z star is. So how would I do this? Well, what I do is just notice that if the area in between them needs to be 99%, then that means the areas out in these little tails have to be 0.5%. And so the area on the left of z star is 99% plus 0.5%, 0.995. So I need to look up a z-score that has an area of 0.995 to its left. So if I'm using a conventional z table, I just look up an entry in the table for 0.9950, or as close as I can get, and then find the z-score that corresponds to that. If I'm using this interactive z table, just drag one of the points all the way to the left end of the axis, and drag the other one around until you get an area of 0.995 to its left. If you do that, you should come out with 2.58. I think you can choose 2.57 or 2.58. Not a big deal. I chose 2.58. Somewhere in between to get exactly 0.995. So, now that we have the z star, the next step is to compute this margin of error thing right here. So usually we just use a formula for that, E, right? I'm just writing this thing down as a formula, E equals z star sigma over root n. So this margin of error is going to be z star times sigma over root n, and now I just fill it in. So in this case, my z star was 2.58. Sigma, this is the standard deviation in the population I'm sampling from. So here I'm given in this question, the standard deviation for weights of individual bricks from the factory is known to be 0.15 kilograms. So I have to be given that number in order to do this. And that's actually, if you think about it, that's kind of silly, because how would we know the standard deviation for the weights of individual bricks from the factory? You would have had to, you know, weigh every single brick the factory makes. And if you did that, you would already know the mean weight for bricks in the factory. So this is kind of a problem, but we'll fix this problem. Don't worry. Soon we'll see how you can fix this problem, and we'll be able to construct a confidence interval from only sample information. This is information about the distribution we're sampling from. Whereas the stuff up here, this 162.4, this is information from a sample. So this is kind of a pie-in-the-sky number, which in the real world you would not get. But don't worry, we'll fix this problem in a sec. But assuming you're given that, assuming you know the standard deviation for all the bricks, weights of all the bricks in the factory, but not the mean, you can calculate this margin of error. We'll do square root of what's our sample size here, 72 bricks in our sample. And if you work this out, this comes out to be 0.0456, I believe. Okay. So that means, so step 1, figure out the value of z star. Step 2, compute the margin of error. Step 3, you can just write down the interval. So with 99% confidence, we have, what do we have? Let's look back. We have this inequality holding. Oops, sorry. This inequality holding. Mu inside this interval x bar minus z star sigma over root n, x bar plus z star sigma over root n. So I'm just going to take my sample mean and add and subtract the margin of error to make the interval. So with 99% confidence, we have mu in here. X bar plus e and x bar minus e. Okay? And so just plugging everything in, x bar was the mean in my sample, 2.256. 2.256. Margin of error, 0.0456. Here, 2.256. Margin of error, 0.0456. And so I end up with, after I do the arithmetic, I think 2.301. 3 decimal places is natural here because this is in kilograms, so this is correct to the nearest gram. 2.201, I think. 2.210, I'm sorry. So with 99% confidence, the mean weight for bricks that come out of this factory, all bricks that come out of this factory, not the ones in my sample. The mean weight of the ones in my sample was 2.256 kilograms. But that's enough information to say that with 99% confidence, the mean weight for all bricks that come out of the factory is between 2.210 and 2.301 kilograms.